Okay, so hi everybody. I'm Assaf. This is joint work with Avinatan Hasidim, and it's about the law of one price for heterogeneous goods. So let me start by saying what is the law of one price. The law of one price states that a good must sell for the same price in all locations. This is trivial for some of us, but some of us are from computer science. And while I call it a law, it's quite obvious that nobody ever gets arrested for selling bananas for half the price, right? It's not an actual law, but we call it a law because the intuition is so obvious and so clear that it should always hold. It's not an axiom, it's not a theorem, it's just obvious that it holds. Because if I want to sell a good for a price which is higher than the market price, I'm just going to get zero profit, I'm going to lower my price. That being said, obviously it's not always true, right? Because I have transportation cost, I can have transaction cost, I can have incomplete information about the value of the good, about where can I find the good that I want to buy, and so on. And obviously, it doesn't hold for heterogeneous goods. What I'll try to show you in this presentation is that it might hold for heterogeneous goods to some extent in most markets. Okay. And from now on, I want you to think about indivisible goods. This is because otherwise it's too simple. And I want you to think about unit demand buyers and unit supply sellers. Okay, this is a technical restriction. It's not very important. So, why the law of one price doesn't hold when we have heterogeneous goods? Okay, so suppose we have two buyers and those are the two buyers, and we have two goods. Okay, so we have honey and carrot, and Winnie the Pooh likes the honey a lot and doesn't like the carrot as much, and Rabbit likes the honey but likes much more the carrot. So in this market, with only those two buyers and two goods, you can have many different price equilibria. You can have both goods selling for the price of 5, okay, and Pooh will get the honey and Rabbit will get the carrot. And you can have honey selling for a price which is much higher than the carrot, or you can have the carrot selling for a price which is much higher than the honey. But in all cases, we'll have the same assignment of Pooh getting the honey and Rabbit getting the carrot. But the price differences are quite different. Okay, the difference between the prices is different, so you don't have a law of one price. Now, what causes it is that the heterogeneity in valuations sort of separates the two goods into two different submarkets. Okay, Rabbit is not really a contestant when it comes to the honey. Okay, he doesn't really pose a threat for Pooh to buy the honey, and similarly about the carrot, but with reverse roles. And the difference in prices can be of the same magnitude as the difference in valuations. Okay? Now what I'm going to show you today is that when we look at heterogeneous goods, but in large market, we sort of get an approximate law of one price. Okay? The difference between the prices becomes small as the markets become large, and this result should depend, because I can just take the Winnie the Pooh and the Rabbit example and multiply it by a lot, okay? And then I will get again price differences. So it should depend on something, and it really depends on the randomness of the market and on the boundedness of valuation. So about the boundedness, I'm going to expand a bit later. As for randomness, you can think about random markets. Most of you are used to think about random markets. You can also think about the interpretation of this as this property, the property of approximate law of one price, holds for most markets. As the market grows large, a larger and larger percent of the markets satisfy this property of an approximate law of one price. Okay, some of them won't, but most of them will. Once you have an approximate law of one price, you can also use it, and I'm previewing the results that I'm going to go over later. But once you have an approximate law of one price, you can also realize that if the market is unbalanced, if you have, for example, more buyers than you have goods, then the prices are going to be very high, because at least one buyer is going to be left out without a good, and this buyer will be willing to pay a very high price for any one of the many goods that she likes. Okay, so some of the goods are going to be priced high, and because of the approximate law of one price, all of the goods are going to be priced high, meaning that the entire surplus is going to go to the sellers and not to the buyers. Okay, so this is a corollary of the approximate law of one price. Yes?
How does it go with the differential prices of this kind of model?
Well, I'm not talking here about the possibility of setting different prices to different buyers, okay? But you can expand the result to some extent to those kind of cases, but I don't want to go into it, okay? Let me move forward by showing you the model, okay? Oh, no, I just want to say that this result, at least for some of you, should remind you of the result of that you get in two-sided matching markets, a recent result that was published actually a few days ago in JP about how you get well, I don't want to say all the surplus, but you get very favorable matching for the short side of the market in two-sided matching market. This is a result by Itai Ashlagi, Yash Kanoria, and Jacob Leshno. So it actually motivated this paper to some extent. Okay, so the model. We have a market with goods and buyers and valuations. We have n goods. We have n plus k buyers, and k could be either 0 or a positive integer, okay? And valuations is just a matrix of real numbers. And for now, think about, well, not for now, for the entire talk, think about this matrix being, each element in this matrix is uniform 0, 1 IID, okay? So, sorry, I have this problem. And it holds for any kind of bounded distribution, which is reasonably nice, okay? But think about uniform 0, 1. Okay. Now, I'm going to say that an assignment of goods to buyers is valid if each good is being bought by exactly one buyer, okay? And all the goods are being bought. This is something that should hold in this model. I can change the definition that it would be maybe more general, but in this case, all the goods are going to be bought because everybody appreciates the goods above 0. Okay, so I'm fine with an assignment with this definition, and I'm going to write that mu of I equals j if buyer I gets good j, and mu of I equals empty set if buyer I gets no good. Okay, and all the goods again are going to be bought because there are less goods than buyers, weakly less. And P is a price equilibrium if there exists a valid assignment such that a buyer doesn't get any good if all the goods, when you take the valuation minus the price, all of them get you a negative number. Okay, so you prefer not to buy a good. And if one of those numbers is positive, then you want to buy that good. Okay, standard definition, I think, or at least should be standard. Here's an example. You have this valuation matrix, and you have an assignment. The assignment is marked with red squares, and a price vector. And this one is not a price equilibrium. Why is it not a price equilibrium? Because you can see that buyer 1 has positive surplus. If you take the valuation minus the price here or here, he's getting a positive surplus, so he wants to buy one of the two goods. Okay, so not a price equilibrium. That's an easy one. This one is a price equilibrium. Okay, and this one is also a price equilibrium. Different prices, but the same allocation. Why do we get different prices but same allocation? Because this is a property of this model that if P is a price equilibrium, then the assignment must be efficient. Okay, this is what the first welfare theorem. It's not exactly that, but it's easy to prove, easy enough to prove. So I removed the proof from my slides. And in our environment, when you take real numbers, generically there is just one efficient assignment. Okay, so any price equilibrium will be using the same efficient assignment. Here is a larger example. Okay, you can easily see, you see the price equilibrium already, but let me just, for your benefit, I'm going to mark it. So this is the price equilibrium, and what you see is that in this example, which is 10 by 10, already when you look at the different prices here, you see that they are not that different. Okay, all of them are about above 0.7. And in fact, there is no price equilibrium. What's that? Well, it's not quite the maximum of 10 uniforms, right? So it should be a price such that each buyer wants to buy exactly one good. So why is it the maximum of 10 uniforms? No, it's not. I don't think that it is. What's that? It shouldn't be. I mean, it doesn't. You know what? Maybe here it is. Maybe here it's not. Here. Look at the last column, okay? 0.71. Almost, yes, but it's not. It's not what. Good. Okay, and here is what I get if I do a simulation. I just randomize markets with different number of goods and the same number of buyers, okay? And I look at all possible price equilibria. Not telling you how to do that, okay? I'm skipping that, but I'm looking at all possible price equilibrium and I look at the biggest difference between any two prices in any equilibrium, okay? And this is how this difference behaves. It goes down as the size of the market grows large, okay? Yes?
I want to understand the statement. So you look at a certain set of prices and said these are close to each other.
What, say?
You looked at a certain set of prices that achieve an equilibrium and said these are close to each other.
Yes.
You want to claim that all set of prices that achieve an equilibrium?
Yes. Yes. So this is exactly. This is for all set of prices. The maximal difference goes down. Okay. Maximum absolute difference. Can Michal? So we proved it for unit demand, but it's not really an important issue. Okay. It's not. I can extend the results for what? I can extend the results to non-unit demand, but bounded demand. Okay, I'll have to have bounded demand. No, it's not. It's not even that. It's not even that. Well, any more guesses? You're going to get there. It's not difficult. You're going to get there. I think the next guess will be right.
It's going to be the log n high.
In log n, right? It's a log n high. Okay, it's going to be the log n high. But that's another way to look at it. But yes. Okay, so here's the theorem. Okay. Well, I said it's joint with Avinatan, right? You give a little, you take a little. Okay, so theorem. There exists a constant. Okay, we know this constant. It's not big. Okay, there exists a constant such that with high probability, with probability that goes to 1 quickly, for any price equilibrium, the maximal difference is at most this constant time log of n over n. So let me just make clear what I mean by with high probability. It means give me a random market, okay? For this specific market, all the price equilibria satisfy this property, okay? So it's not for most price equilibria, it's for most markets. And this, again, what I said before, that you can think about it holding for almost all the markets as the markets grow large. Intuition. Okay, so this is for the economist around. Okay, so the intuition is. What's that?
When the market is balanced, includes k equals 0.
Includes k equals 0. Could be for k bigger than 0.
Sorry?
Could be for k bigger than 0.
The problematic one will be k equals 0 when it's balanced. And there is always
Well, apparently it's not. Okay, maybe, but it's not a problem for k equals 0. So intuition for economists, and then intuition for computer scientists. Okay, intuition for economists. Rabbit is not really a contestant for the honey that Pooh wants, right? And any two take a pair of two goods that are sold in different prices, it's not necessarily true that the buyer who buys the good that is sold for the high price necessarily wants the good that is sold for the low price, right? Because maybe she just doesn't like that good, okay? But if there is a buyer that buys a good for a high price, it should be true that all other goods that that buyer likes are also high priced, right? So now we have a lot of goods with high price and a lot of buyers that pay a high price. If we have another good which is low priced, then there could be potentially many buyers that want that good, okay? So all of them should be paying low prices. So now we have a lot of buyers that are paying high price and a lot of goods that are sold for a low price, and that should already be some kind of contradiction. Okay, this is for economists. Now for the computer science guys. most of you. So here's the proof, okay? Assume the markets are balanced, okay? The difficult case, probably. So let P be some price equilibrium, and think about a buyer who's buying currently good J, okay? Currently is assigned to good J, but his valuation for good J prime is also very big as 1 minus delta. Then, because of the same argument that I just told you, the price of good J prime should be at least as high as the price of good J minus delta, okay? Otherwise, the buyer would want to buy J prime instead of J, okay? Now, this means this is exactly this relation. We have a good that priced at Pj, and if the buyer likes this good 1 minus delta, then the price here should be big, okay? Also true that if we have a good and a buyer in the middle, okay, such that this buyer likes good J star 1 minus delta 1, and buyer I star like good J prime 1 minus delta 2, then the difference in prices between those two should be at most delta 1, okay? And this one should be already, I use the lemma twice, and I get that price of J prime should be price of Pj, price of J minus delta 1 plus delta 2. So now, computer science guy, what do I need to do? I just need to take this graph, right, and find a path between any two goods such that the weight on this graph would be, well, such that the deltas on this graph, the sum of them would be small, right? And then I can see that the difference between prices is bounded from below. And I'll do it for both sides, so I'll have the absolute difference bounded from above. Well, we solved it, and then we found the answer already in the literature, that with high probability for any assignment, okay, and that's important because I never said anything about the assignment being the optimal one. But for any assignment, the weighted diameter of the relevant graph is at most C log n over n, and that's it. That's the end of the argument. Now, we extend it for different distributions and for unbalanced market, but that's enough, okay? Is the proof clear enough? I mean, apart from this part, right? But this one you can go and read. What's that?
Do you have any assignment? So what's the probability?
Sorry. The probability is about the markets. Take a random market, okay? Take a random market with high probability for any assignment. This is true. The diameter is small. For any valid assignment. Yes, sorry. For any valid assignment. Okay, good. Now we can also bound the difference from below. I'm not going to show you how, but I can show you that with high probability, there is a price equilibrium such that there is a difference of at least C log n over n between two prices. Okay, so this is higher bound, upper bound, and lower bound. Okay, and I promised you something about the surplus. So here's the surplus. If we look at the balanced market, the surplus of the buyers could be as high as that. Okay, they can get almost 100% of the surplus. That's if the price equilibrium is very low. Okay, the prices are very low, but all prices are very low. And it could be a very small surplus if all the prices are very high. On the other hand, if there are more buyers than sellers, then always the surplus will be small. The prices will be very high. Nick, you have a question?
So yeah, just to make sure I'm understanding. Basically, when K equals 0, you have a situation where, depending on the realization of the preferences, you may have a market where all equilibria involve large surplus for one side, or a market where all equilibria involve large surplus for the other side.
No, that's not what I'm saying. No, sorry. That says for most realizations, okay, with high probability over realizations, for most markets, you can have both types of equilibria. Okay? There are good prices and bad prices for the buyers.
Oh,
Okay?
okay.
In each equilibrium, all the prices are very similar, but in one of them they're all high.
Yeah. Yes. So that's true for most markets. And there is a small percentage of market for which it's not true. Okay? It might not be true.
If I want to take normal distribution instead of uniform
So you want unbounded distributions.
For some of them will work. You have some
Yes.
extension. So is normal one when it
Well, no. My extension is going to be it's not working for unbounded distributions, but it will work for certain unbounded distributions.
So the answer for normal is no.
For normal, I think it's no. Yes, it's no. For normal, it's no. Okay? But you mean log normal probably, but no.
I don't know. I mean, the point is that things have to bunch up to close to the boundary. That's when the deltas become small. And so the question is how much can you allow the boundary?
Yeah, that's the problem with lecturing to Sergio, right? I mean, I could stop at the first slide. Okay, let me go ahead, even though you also already heard this talk, so maybe it yes. So discount that just a bit, okay? Discount just a bit. Okay, so corollary, with high probability, if the market is balanced, then there exists a constant such that the maximal price is not that high, meaning that all the surplus goes to the buyers, okay? Proof, how much time do I have? What's that? 10 minutes. Let me skip that. Okay, it's easy to prove. And on the other hand, if market is unbalanced, then all price equilibria are going to be high. Okay, all the surplus goes from the buyers to the sellers. Let me relate that to the core of the assignment game because that was our initial motivation, at least. So the assignment game is the same metrics that you see, and you have buyers and sellers. Okay, and you try to find co-allocations, meaning that coalitions shouldn't be able to deviate and create their own small surplus, and which will be bigger than what they get under the assignment and the different payoff vectors that they get. And in fact, in this model, if P is a price equilibrium, then the relevant assignment plus P plus what the buyers get is a co-allocation, okay, and vice versa. So price equilibrium here means co-allocation in the assignment game. And in the assignment game, you have this nice core, which looks something like that. And it's a big one. And then what we showed you now, what you saw just now, means that all prices are very similar, okay? But they could be varying from being low to being high, right? So you have a very narrow core, okay? Something that looks almost like a line. And in unbalanced markets, you actually get a very small core. You get core convergence because you know that the prices are going to be high, and you know that all the surplus is going to go to the sellers. Okay, so this is what the core looks like for this game. Okay, now let me talk about what happens when we have complementarities between buyers and sellers. That relate to a question that was before in Nick's presentation. Up until now, I assumed independence, right? Everybody likes different goods differently, okay? But there could be good goods and bad goods, right? There could be high quality goods and low quality goods. So, and there could be different buyers that care less or more about quality. So suppose that we have valuations that depend on, again, this kind of idiosyncratic variable, okay, this IID variable, but also some kind of quality. If the quality is just linear in the valuation, okay, then there is no difference because everybody sort of, everybody is willing to pay QJ more for good J, okay, that's not an issue. But if there is some kind of interaction between the quality and how much a buyer likes quality, then things become complicated because there is going to be some kind of assortative matching. Okay, the high quality goods are going to go to buyers that like quality. Okay, but there is also going to be some kind of matching there is also going to be a dimension of idiosyncrasy, of heterogeneity. Okay, so it's going to be more complicated, but still with heterogeneous goods, and even with goods of different qualities and buyers have different taste for qualities, an approximate law of one price continues to hold. Now, it should be clear what I mean by an approximate law of one price here, because goods that are of high quality should be sold for a higher price, right? So the law of one price here said that if you have similar quality, if two goods are of similar quality, they should be sold for similar price.
ratios?
Ratios between what and what?
Like if you have two goods that have a certain ratio between their quality.
So let me show you the result. I'll show you the statement at least, okay? And then you'll tell me what's missing, okay? So I'm looking at a benchmark model because this one is very difficult to do generally. I think it also shouldn't hold generally, but it should hold when, for example, you have multiplicative complementarity between the goods and the buyers, okay? And in this model, we first show associative matching, meaning that the difference between the quality and the taste for quality shouldn't be too high, okay? That's what you'd expect, okay? You'd expect that high quality goods go to buyers that appreciate quality. And then the law of one price says that if the difference between qualities is not too big, then the difference between prices is not too big. Now tell me what you meant here. You meant that here I'll have like ratio instead of difference? Yeah, okay, good. So that's what we know how to prove, but this one is, I'll keep it for Noam's seminar in next semester, the proof, okay? So Noam will see it, and everybody else can come in, April, whatever. Here's the surplus distribution in those markets with complementarities. Again, when the market is balanced, then it could be that the good is sold exactly for what it's worth in terms of quality, okay? And it could be that all the surplus go from the idiosyncratic component also goes to the sellers, okay? There could be that one or that one, but if we have unbalanced market, then definitely all the surplus goes to the sellers again, okay? And what do the buyers get? They only get their quality, okay? The test for quality. Let me skip that because I want to get to that one that Sergio was wanted to see. Evaluations are IID, but with unbounded support now. Okay, we have, for example, normal distribution, exponential distribution, whatever distribution that says that values in the matrix can become high. What's the economic intuition for that one? It means that some goods are appreciated by one buyer or two buyers or three buyers much more than they are appreciated by all other buyers, and much more than those buyers appreciate other goods, okay? So you can find, for example, two buyers that will be willing to pay a very high price to get that specific good and not another good, okay? That means that this good, the price of that good should be high in any price equilibrium, right? Because two buyers are just going to compete on it. On the other hand, there would be goods that wouldn't be very highly valued by any seller. Okay, so their price could be close to zero. And when you have this kind of unbounded valuations, the law of one price may not hold. It could be that there is a big difference. Specifically, if you take the exponential distribution, we can show that with high probability, there will be a price equilibrium in which the difference between Pj and Pj prime for two specific goods is going to be of order of magnitude of log n, and this is also going to be the expected surplus in this market, okay? Meaning that a lot of the surplus in a specific transaction goes to the seller, but in another transaction, most of the surplus goes to the buyer, okay? So different prices by an order of magnitude. That's it. I'll conclude here. I'll say just that what we showed you was that an approximate law of one price continues to hold for heterogeneous preferences. Okay, so for those of you who did study economics, think about Econ 101. Okay, you have 10 farmers, 11 sellers with bushels of wheat. Okay, you remember that word, bushels, right? Am I saying it right? Bushels, whatever, wheat. Okay, we used to say that the buyers are going to get all the goods because there are 10 of them and 11 sellers, right? But that was for homogeneous wheat. And apparently it's also true for rye and whatever, and silva, and whatever other kinds of wheat that you have, okay? It's true for heterogeneous goods. In the IID case, convergence is quick. When you have complementarities, the convergence becomes slower, but not much slower. It's still 1 over square root of n, or n to some power, okay, between 0 and 1. And with unbounded valuations, the law of one price can fail. And let me put the literature review now, because that's how Sergio likes it, right? So I already mentioned this is the transferable utility parallel of the result by Yashkanoria and Ita-Ashlagi. Yeah, that should be Ashlagi et al. Ita-Ashlagi and Yashkanoria and Jacob Leshno. And as I said, it came from the literature on assignment games. Okay, this used to be about assignment games, but then I realized that it's just true for any kind of price equilibrium, which makes it nice. And it also relates to the results on convergence of the core in two-sided matching markets that are usually explained by either short preference list or by correlated preference, and you saw both of those, I guess, in Nick's talk, or just, as I said, unbalanced market. That's it. I think we'll move to questions if you have any.